Okay.
Okay, I think that's most people back and joining us. Good afternoon, everyone. I'm going to talk a little bit now about writing your own protocols and give you a quick demo of how to upload new protocols to the system. I noticed quite a few of you have been doing that already, so well done. It's nice to know that it's possible to do without too much instruction. Hopefully this will give you a bit more of an overview of how protocols are written. I'm not going to go into every little detail now. For some aspects, there are lots of comments in the protocols on the web lab that you can then adapt based on that. There'll also be another talk tomorrow morning, which goes into some more details of the post-processing operations that are possible. But for now, I'll give sort of an overview with this diagram we saw before of the structure of a protocol, just give you a bit more about what goes in to the different sections here, and then I'll walk you through one example from the web lab to show you where the different bits appear in the file, so you get kind of a bird's eye view of how a protocol is structured to help you orienting and looking at other protocols and starting to develop your own. So the model interface section, we've already mentioned most of this. I think the challenges from wanting to apply one protocol to a range of different models. And so we've talked about using ontologies for consistently labeling variables. And another challenges that comes up is different ways of representing the biology. And that's particularly often with currents. There are 3 different conventions for currents. Either it's whole cell current measured in amps, or it's normalized by the membrane capacitance or the membrane surface area. And so you get not just a scaling of units within one dimension, you've got completely different dimensions that you need to convert between. So there's some support for handling that in the system as well, and for isolating subcomponents of the model. So the units conversion is possibly the least intuitive in a way in some senses. You've got different models using different units, and so in the protocol file, you'll declare the units that the protocol is interested in, and the software will automatically scale from model units to protocol units and vice versa at the inputs and outputs between them. And where you don't have a simple scaling, you can actually define in your protocol biology-aware conversion rules. So you can say, if I've got a current in amps and I want my current normalized by capacitance, what I need to do is divide by the cell capacitance as given in the model, and then I've got something that's in the right dimensions and I can scale it. So within a protocol, you can actually define those kinds of rules that say, if I've got something in this dimension, I want to get something in this dimension, this is the rule for converting those values. And the system will actually fall back to other rules. If you don't have in the model some of the biology you need to apply that sort of conversion, it can try something else. So we'll see, there are some examples of that in quite a few of the protocols for dealing with current units. Another part of the model interface is dealing with modifying models, particularly sort of extract just the portions of interest. And this works on an abstract basis. So the model is viewed not as a CellML file or a particular syntax, but just as a system of equations. It's a system of ordinary differential equations, and the modifications operate on that system. So we specify inputs and outputs for the model. Inputs become parameters that the protocol can set. Either it might be that the variable is a state variable and you want to let it continue being a state variable and varying, but just at some time points you want to be able to change it instantaneously. Or it might be that you want to throw away the equation and make it just a fixed parameter of the model, and both of those are supported. And only the equations needed for the particular outputs are actually evaluated, as we've mentioned before. And you can also, at that sort of abstract level, define new equations. So you can give a new definition for any variable, and either that will become a new equation in the model if the variable wasn't there before, or it will replace the existing definition if the variable was there. So you can alter the mathematics of the model in any way you choose from the protocol. And the most common example of that is just putting in different stimulus current waveforms. But you could do many other things if you needed to. And with all of these, you specify a whole bunch of interface rules, inputs, outputs, new equations, and so on. And the software tries to do the right thing, so you get a sensible model representing what you're interested in at the end of it. Most of the time it does a good job. A couple of you have noticed with some models that there are edge cases where it's hard to decide in a given instance which was the right thing to do, or at least what the author intended. That particularly comes if you're specifying something as an input that is actually a computed value. So it's computed by an equation in the model rather than being a parameter or a state variable. And you want to say, I want this to be an input that I can change, but I'm not specifying that it's clamped to a particular value. And the system doesn't allow you to do that at the moment because it's just too ambiguous as to what you might actually want it to do. So I believe that's something that we can change if we can decide on exactly what should be the right thing to do in that kind of situation. So next big component of the protocol is the simulations that you want to run. The basic case is a time course solve for model equations. So that's one kind of simulation. Experiments can have a setup and then a measurement phase. So we're allowed to do multiple simulations within a protocol, not just one, and those run in sequence on the model. And you can also nest simulations within loops so that you can run multiple time courses, doing parameter scans, repeated runs, distributed sampling, any kind of repetition is supported by that construct. And as I mentioned, this means that the outputs from simulations are always regular n-dimensional arrays, and that's the data type that's operated on. With both kinds of simulation, whether it's time course or nested, you can have two extra bits that you specify. You always need to give a range for the simulation, which basically says, what are we iterating over for output points of interest. So in a time course, what time values? In a nested loop, what arbitrary values are we iterating over? And there are different kinds of range that you can give. And you can also specify a collection of modifiers which let you change or record the state of the model. So you can either change a particular variable at each iteration of the loop, you can save the entire state of the model, or you can reset to a previously saved state. Then once you've got some raw simulation outputs, there's a lot you can do to post-process those. And here, a lot of it I'm actually going to defer to tomorrow morning. We won't go into details this afternoon. But I just noticed one sort of design consideration that's led to the language being the way it is. We started this off wanting a system where the protocol descriptions could be exchanged between different software infrastructures. We didn't want, partly for security considerations and partly for that sort of exchange purpose, to just say, you've got a general purpose programming language here, you can do anything. Because that's hard for other people to implement, as they just stick a full programming language implementation in there. And it's also hard for security if we're letting people upload protocols that can do anything to run on our servers. That's a bit of a risk. So we've got a language that's not a full general purpose programming language. There's a restricted set of things that you can actually do with it, but it still needs to do complex post-processing operations. And that's particularly the case for cardiac, because pretty much the first thing you want to do with a cardiac simulation is compute actual potential duration. And this is one of the most fiendishly complicated post-processing operations that I know of, and it's really hard to do and to do right. So you actually need quite a complex language, but still something that's not too complex. And so a lot of the way it's been designed has been trying to balance those two goals. One other thing that's worth commenting on before we look at some examples is referencing variables. So you've got all these different sections of your protocol. You've got the outputs, post-processing, the raw, simulations, imports from other libraries. And within a given place, say in an output, you might want to output something that's computed in the post-processing section. You might want to output something that was a result of a simulation. You might want to output something that's just a variable from the model. And so you need to have a way of referencing all these things in different places within the system. So that's what this diagram tries to encapsulate, which is in the reference materials on the website. This is the name resolution diagram. And this basically explains where, if you've got a reference to a variable with some sort of name, where is that found? We use a general colon-separated naming scheme. So your variables might just be a name, to basically look up a variable in the same place as where you are, look up something just from post-processing, that's where you are. But you can also do prefix colon name to look up something that's defined elsewhere. And partially that's done with our ontologies. So we can actually have short form prefixes associated with a particular ontology, and then you can look up names within that ontology. Anyone familiar with some XML or HTML will probably recognize this kind of idea. I stole it from that language. And you can then chain these things. So if a simulation has a particular name, you can look up stuff as a result of that simulation, or in this case, we're looking up a few levels up. So basically, you read the diagram by saying, okay, if I'm in post-processing here and I just put a variable name, I'm going to first look for things that are defined in the post-processing section. If I don't find the variable there, I've got a solid arrow, so I'm going to look in my protocol library and see if there's something with the same name defined there. If it's not there, I follow the solid arrows to find if there's a protocol input with that name. If I have a colon name, a prefix colon name, I start following the dotted arrows at some point. So if I have either an imported protocol or a simulation that has a name matching, say here, sim, okay, I've got a simulation called sim, so I'm going to follow the dotted line to that simulation's results and look for the name there. In this case, I've actually got an ontology term, I've got an extra prefix here, so I've got another dotted line taking me straight to a model variable that I'm then looking up. So basic names follow the solid arrows to find them, and then dotted arrows take you down a prefix to find variables. Hopefully that become a bit more clear with some examples. I'm going to go through one now. So all of the protocols in the Web Lab have quite extensive comments to try and walk you through what they're doing and explain how it's working. I'm not going to go through all the details of all the examples. I'm just going to take one, do the regular 1 Hertz pacing to show you how that works out. So steady state 1 Hertz pacing, which I've seen here is the protocol, and we've got 3 files that are making up this protocol, plus the documentation bit that gets displayed down here. The one that's highlighted is the main file for the protocol, so that's where we're going to start. We're going to have a look at what that says. And we've got quite a few comments with hash lines, the documentation that gets displayed about the protocol, and then the protocol itself, the actual bit that does something, is just these 4 lines down here at the bottom. In this case, it's a protocol import. So we're saying we're actually importing another protocol file, steady state runner, and this protocol is going to behave exactly like that one, except that 2 of the inputs are changed. So we're overriding the pacing period and the num inner paces to say we've got 1 Hertz pacing and doing 2 paces at each iteration. So next we then look at the steady state runner to find out what's going on. And here again, we've got some documentation in case this is being used just by itself or to give people an idea of what to do with it. And then we start seeing more of the different bits that can come in a protocol. This has actually got some stuff in it. So we've got, first of all, here a namespace prefix binding. So this is where I've said that this oxmeta prefix that I can use for variable references means the long URI for our ontology. So now I've got just a short name for referring to things in that ontology. I'm defining the inputs to this protocol. So those are things that can be overridden if the protocol is imported. And some of those, they all have default values given. And then I'm importing some protocols. So this time, rather than just importing and overriding their units, I'm actually assigning these imported protocols to some prefixes because these are libraries of post-processing functions that I want to use. So I'm just naming these as prefixes. So now I can refer to, say, functions in this library by std : the name of the function when I use that later on in the protocol. I have a library section here that's just defining, I can define variables, I can define functions. In this case, I've got one variable defined for convenience later on to divide the maximum number of paces I'm allowed to perform by the number of paces at each iteration to find out how many iterations I want to run. I've got units definitions to say what the units are as far as the protocol is concerned that it's interested in, looking at milliseconds, millimolar, and so on. There's no model interface within this protocol that would normally appear next. That is actually defined in the third file, the single pace protocol, that we'll come to later. So that's one point to note. Often the model interface that's used isn't necessarily up near the main protocol. It might be buried quite a few levels down. What we do have is some simulation tasks. And in this case, we've got a couple. The first one is responsible for getting the model to steady state. And then the second one down below will be looking at what the action potential looks like at that steady state. So this first simulation is a nested simulation. And here we've got the range. The variable name is called paces, multiple paces. Its units, just dimensionless, it's a plain number. And the type of range it is a while loop. So you've got uniform ranges, vector ranges, we'll see. In this case, it's a while loop, which will continue running as long as some condition is met. In this case, as long as the model is not in steady state and we haven't given up yet. And then each time around that outer loop, we're running another protocol. So here we're nesting not simulation, but an entire protocol, single pace.txt, which gets run each iteration around this loop. And we change some of its inputs to reflect the number of paces we want it to run and the pacing period. And we select which outputs of that protocol are of interest. So it might compute quite a few things. Those are the only two that we actually want to record and analyze within this protocol. And then here we have the second simulation in this protocol called detail here. And this time it is just a straight time course simulation of the model that's running a uniform time course, time measured in milliseconds. And it's running basically for this number of milliseconds with one of the protocol inputs that gives you 1 or 2 paces to analyze at a finer time resolution. We haven't specified a resolution here, it's just defaulting to 1 millisecond. Then we have the post-processing section with variable assignments. We'll look more into how you write those and adapt them tomorrow morning, but read through the comments to see the kind of things that are available, all the arithmetic, but also extra operations for operating on those n-dimensional arrays. So I'm not going to go into any detail of that this afternoon. And then we have the output specification. What are the outputs of interest from this protocol? And there are quite a few of them that we're listing. For things that were defined in the post-processing, we're just giving their name, specifying what their units are, because that information isn't available, and giving a human-readable description for each variable. For things that are raw simulation results that we still want to output, we need to give them a name as an output and then reference them with a variable reference to pick out the appropriate variable from which simulation it was, which result it was. And some things are given as optional. You can't quite see off the bottom of the screen. In this case, for calcium-related outputs, because not all models represent intracellular calcium, that's given as optional. The outputs will be produced if they exist, and if they don't exist, that's not an error. The protocol just ignores them. And then finally, the things that you want to plot as a result. All plots have a name. You specify whether they're just continuous lines or lines with points or isolated points. And then what is actually getting plotted is off the right-hand side of the screen there. So it's always y against x. And sometimes you can have a key variable as well if you're plotting multiple lines. Again, see some of the comments in existing protocols for examples of that. The things that you plot here all have to be defined as outputs of the protocol to be available for plotting. And then we'll just go to that single pace protocol that was in the nested simulation to show you that here we've got various things again, the namespace bindings, some inputs declared, importing standard library units and so on. But now here we've got the model interface. So this is where we're saying what the protocol expects of the model, what it's going to change, what it's going to read. So we can say we've got a couple of inputs in this case, and we're using a sort of prefix annotated names to say it's in the oximeter ontology, we declared above, and it's the term membrane stimulus current offset. We're going to consider it to be in units of milliseconds. Conversions will be applied, and we're going to say its initial value is 0. Throw away whatever was given in the model. Similarly for the stimulus period. We also say below what model outputs we're interested in, so the membrane voltage and time, and the units that we want those in. This other output here, oximeter state variable, is worth a brief mention. That one isn't an explicit annotation on any variable. That one is added implicitly by the tool to everything that is a state variable. And so when you read that output, you're not getting just one variable, you're getting a vector of variables. So over a time course simulation, that actually gives you a 2D array for all the state variables over all time points. That the same sort of behind the scenes mechanism can work if you do have an ontology term that annotates explicitly multiple variables. You can still use it as an output to get a vector and values output from your model as one variable. We have the calcium being read, and this is marked as optional, so it's not an error if it doesn't exist. And we are changing the stimulus current definition by just defining a new equation for the membrane stimulus current ontology term. So any definition of this variable in the model will be thrown away, and this equation will be used instead, which partly picks up the offset and period that we mentioned as inputs earlier, partly picks up just some other variables in the model, amplitude and duration, which aren't specified as inputs or outputs, but must exist within the model in order for this particular stimulus equation to work. So it's reusing the stimulus amplitude and duration for the pulse, but just changing the frequency at which that pulse is applied, essentially. And then again, we've got similarly simulation tasks in here, post-processing, outputs, plots, and so on. So that gives you a sort of little overview of one protocol, what sort of bits go into it, how they're arranged in the files, and you can work through the others to adapt them to different scenarios. There are various suggestions for things to look at in the practical tasks that you can have an experiment with. And I'm just going to do a quick demo of adding a new protocol to the system. So firstly, I'm going to take this 1 Hertz protocol that I've got here, and I'm going to save those 3 files to my computer. So I've got them locally. And then normally you would go and edit these to produce something similar, maybe did a different pacing rate or varied something else. In this case, I'm just going to upload the same protocol again. So to log in again, because I didn't check the Remember Me box. I got logged out. There we go. Right, so again, I'm going to the My Files page, but this time the Protocols tab, and I can create a new protocol. Give it a name of some sort. Note that I think quite a few have been noticing names have to be unique across the whole system. So if you've put in the name of a model and someone else tries to upload the same model, you'll probably get a conflict. That's something we might look at changing, but it's a bit difficult to decide once things go public which one should have that name if you allow for duplicates. And then we come to add some files to this. So I'm going to go and add each of those 3 files to make up the protocol. You can drag and drop as well, which is often a quicker way of getting multiple files in. And importantly, I have to say which one is the main file for this protocol, so which is the outermost one that imports the other ones. And I can then go and create the protocol. Excellent. I have a new protocol. You can go and have a look at it. And there it is. If I wait a moment and just refresh that, I should see, come up in a few seconds. This little note, all protocol files parsed successfully. So when you upload a new protocol, it launches the background job anywhere in the system, actually, to try parsing the protocol file and check that you've got the syntax correct. If you have, it adds that note to the record. If you haven't, it adds an extra file to your protocol with a list of all the errors it found trying to parse it. So that's quite useful to check for before you start running experiments, just to make sure that the protocol will actually pause and do something before you run separate experiments and they all become red because it can't read the protocol file properly. So having got my protocol file, I can then go and run this on some models. And let's go and run it on the demo one that I added earlier today. And there we go. It is running. It is queued. Nope. Status running. And I just have to wait for it to finish.
So can you edit the protocols once you've uploaded them, or do you have to edit them offline and then?
You have to edit them offline and then upload a new version. So I can, rather than having to create a new protocol each time, got my protocol description here, the model, protocol version. Similarly with models, I can see different versions of it and just add a new version of that protocol. But you do then need to upload again all the files that make up the protocol and select which one is the main one. I think several people have already added a commented feedback saying this is less than ideal. But that's the way it is at the moment.
The only files that are shared between protocols are your magical, like Cardiac library. So
yeah.
Hidden.
So yeah, the basic library and the Cardiac library is built in. There are links in the practical description document. Yeah, within the reference manual, it links to the files, and also within quite a few of the comments, it gives you direct links to view those files to see what actually is available in them and how they're defined. And we'll look at them a bit more tomorrow.
I guess there would be, if you have a user's library, single ASP workload instead of uploads.
Yeah, and it's one thing we've considered doing, actually having protocols that can import other protocols within the system rather than just files defined locally. Basically, once you do that, you have to have a proper distributed version control system. I didn't fancy implementing that for the first version. Any other questions? Have fun trying it out.